Polynomial and rational functions. Digital photography has dramatically changed the nature of photography. No longer is an image etched in the emulsion on a roll of film. Instead, nearly every aspect of recording and manipulating images is now governed by mathematics. An image becomes a series of numbers representing the characteristics of light, striking an image sensor. When we open an image file, software on a camera or a computer interprets the numbers and converts them to a visual image. Photo editing software uses complex polynomials to transform images, allowing us to manipulate the image in order to crop details, change the color palette, and add special effects. Inverse functions make it possible to convert from one file format to another. In this chapter, we will learn about these concepts and discover how mathematics can be used in such applications. Curved antennas, such as the one shown in Figure 1, are commonly used to focus microwaves and radio waves to transmit television and telephone signals, as well as satellite and spacecraft communication. The cross-section of the antenna is in the shape of a parabola, which can be described by a quadratic function. In this section, we will investigate quadratic functions, which frequently model problems involving area and projectile motion. Working with quadratic functions can be less complex than working with higher degree functions, so they provide a good opportunity for a detailed study of function behavior. Recognizing characteristics of parabolas. The graph of a quadratic function is a U-shaped curve called a parabola. One important feature of the graph is that it has an extreme point called the vertex. If the parabola opens up, the vertex represents the lowest point on the graph or the minimum value of the quadratic function. If the parabola opens down, the vertex represents the highest point on the graph or the maximum value. In either case, the vertex is a turning point on the graph. The graph is also symmetric with a vertical line drawn through the vertex called the axis of symmetry. These features are illustrated in Figure 2. The y-intercept is the point at which the parabola crosses the y-axis, and the x-intercepts are the points at which the parabola crosses the x-axis. If they exist, the x-intercepts represents the zeros or roots of the quadratic function, the values of x at which y equals 0. Understanding how the graphs of parabolas are related to their quadratic function. The general form of a quadratic function represents the function in the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers, and if a does not equal 0, if a is greater than 0, the parabola opens upward. If a is less than 0, the parabola opens downward. And we can use the general form of a parabola to find the equation for the axis of symmetry. The axis of symmetry is defined by x equals negative b divided by 2a. If we use the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a, to solve ax squared plus bx plus c equals 0 for the x-intercepts or zeros, we find the value of x halfway between them is always x equals negative b over 2a. The equation for the axis of symmetry. Figure 4 represents the graph of the quadratic function written in general form as y equals x squared plus 4x plus 3. In this form, a equals 1, b equals 4, and c equals 3 because a is greater than 0. The parabola opens upward. The axis of symmetry is x equals negative 4 over 2 multiplied by 1 equals negative 2. This also makes sense because when we can see from the graph that the vertical line, x equals negative 2, divides the graph in half, the vertex always occurs along the axis of symmetry. For a parabola that opens upward, the vertex occurs at the lowest point on the graph. In this instance, negative 2, negative 1. The x-intercepts, those points where the parabola crosses the x-axis, occur at negative 3, 0 and negative 1, 0. The standard form of a quadratic function represents the function in the form f of x equals a multiplied by x minus h raised to the second power plus k, where h and k is the vertex. Because the vertex appears in the standard form of the quadratic function, this form is also known as the vertex form of a quadratic function. As with the general form, if a is greater than 0, the parabola opens upward and the vertex is a minimum. If a is less than 0, the parabola opens downward and the vertex is a maximum. Figure 5 represents the graph of the quadratic function written in standard form as y equals negative 3 multiplied by x plus 2 raised to the second power plus 4. Since x minus h equals x plus 2 in this example, h equals negative 2. In this form, a equals negative 3, h equals negative 2, and k equals 4 because a is less than 0. The parabola opens downward. The vertex is at negative 2, 4. The standard form is useful for determining how the graph is transformed from the graph of y equals x squared. Figure 6 is the graph of this basic function. If k is greater than 0, the graph shifts upwards, whereas if k is less than 0, the graph shifts downward. In figure 5, k is greater than 0, so the graph is shifted 4 units upward. If h is greater than 0, the graph shifts downward the right, and if h is less than 0, the graph shifts to the left. In figure 5, h is less than 0, so the graph is shifted 2 units to the left. The magnitude of a indicates the stretch of the graph. If the absolute value of a is greater than 1, the point associated with a particular x value shifts farther from the x-axis, so the graph appears to become narrower, and there is a vertical stretch. But if the absolute value of a is less than 1, the point is associated with a particular x value shifts closer to the x-axis, so the graph appears to become wider, but in fact there is a vertical compression. In figure 5, the absolute value of a is greater than 1, so the graph becomes narrower. The standard form and the general form are equivalent methods of describing the same function, and we can see this by expanding out the general form and setting it equal to the standard form. A multiplied by x minus h raised to the second power plus k equals ax squared plus bx plus c. Ax squared minus 2ahx plus ah squared plus k equals ax squared plus bx plus c. For the linear terms to be equal, the coefficients must be equal. This is the axis of symmetry, and as we defined earlier, we set the constant terms equal. And in practice, though it is usually easier to remember that k is the output of the value function when the input is h, so f of h equals k. Forms of quadratic functions. A quadratic function is a polynomial function of degree 2. The graph of the quadratic function is a parabola. The general form of a quadratic function is f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a does not equal 0. The standard form of a quadratic function is f of x equals a multiplied by x minus h squared plus k, where a does not equal 0. The vertex hk is located at h equals negative b divided by 2a. K equals f of h equals f of negative b divided by 2a. Finding the domain and range of a quadratic function. Any number can be the input value of a quadratic function. Therefore, the domain of any quadratic function is all real numbers. Because parabolas have a maximum or minimum point, the range is restricted. Since the vertex of a parabola will be either a maximum or a minimum, the range will consist of all y values greater than or equal to the y coordinate at the turning point or less than or equal to the y coordinate at the turning point, depending on whether the parabola opens up or down. Domain and range of a quadratic function. The domain of any quadratic function is all real numbers unless the context of the function presents some restrictions. The range of a quadratic function written in general form, f of x equals ax squared plus bx plus c, with a positive value is f of x is greater than or equal to f of negative b divided by 2a, or f of negative b divided by 2a, and infinity. The range of a quadratic function written in general form with a negative a value is f of x less than or equal to f of negative b divided by 2a, or negative infinity to f of negative b minus 2a. The range of a quadratic function written in standard form, f of x equals a multiplied by x minus h squared plus k, with a positive a value is f of x is greater than or equal to k. The range of a quadratic function written in standard form with a negative a value is f of x is less than or equal to k. Determining the maximum and minimum values of quadratic functions. The output of the quadratic function at the vertex is the maximum or minimum value of the function. Depending on the orientation of the parabola, we can see the maximum and minimum values in figure 9. There are many real-world scenarios that involve finding the maximum and minimum value of a quadratic function, such as applications involving area and revenue. Power functions and polynomial functions. Suppose a certain species of bird thrives on a small island. Its population over the last few years is shown in Table 1. The population can be estimated using the function p of t equals negative 0.3 t raised to the third power plus 97t plus 800, where p of t represents the bird population on the island t years after 2000. We can use this model to estimate the maximum bird population and when it will occur. We can also use this model to predict when the bird population will disappear from the island. In this section, we will examine the functions that we can use to estimate and predict these types of changes. Identifying power functions. Before we can understand the bird problem, it will be helpful to understand a different type of function. A power function is a function with a single term that is the product of a real number, a coefficient, and a variable raised to a fixed real number. A number that multiplies a variable raised to an exponent is known as a coefficient. As an example, consider functions for an area or volume. The function for the area of a circle with radius r is a of r equals pi r squared, and the function for the volume of a sphere with radius r is v of r equals 4/3 pi r cubed. Both of these are examples of power functions because they consist of a coefficient pi or 4/3 pi multiplied by a variable r raised to a power. Power function is a function that can be represented in the form f of x equals kx raised to the p power, where k and p are real numbers and k is known as the coefficient. Identifying end behavior of power functions. Figure 2 shows the graphs of f of x equals x squared, g of x equals x to the 4th power, and h of x equals x to the 6th power, which are all power functions with even whole number powers. Notice that these graphs have similar shapes, very much like that of the quadratic function in the toolkit. However, as the power increases, the graphs flatten somewhat near the origin and become steeper away from the origin. To describe the behavior as numbers become larger and larger, we use the idea of infinity. We use the symbol infinity for positive infinity and negative infinity for negative infinity. And we say that as x approaches infinity, which can be symbolically written as x approaches infinity, we are describing a behavior. We are saying that x is increasing without bound. And with the positive even power function, as the input increases or decreases without bound, the output value becomes very large. Positive numbers, equivalently, we could describe this behavior by saying that as x approaches positive or negative infinity, the f of x value increases without bound. In symbolic form, we could write as x approaches positive or negative infinity, f of x approaches infinity. Figure 3 shows the graphs of f of x equals x cubed, g of x equals x to the 5th power, and h of x equals x to the 7th power, which are all power functions with odd whole number powers. And notice that these graphs look similar to the cubic function in the toolkit. Again, as the power increases, the graphs flatten near the origin and become steeper away from the origin. These examples illustrate that functions of the form f of x equals x to the nth power reveal symmetry of one kind or another. And first, in figure 2, we see that even functions of the form f of x equals x to the nth power and is even, are symmetric about the y-axis. In figure 3, we see that odd functions of the form f of x equals x to the nth power and odd are symmetric about the origin. And for these odd power functions, as x approaches negative infinity, f of x decreases without bound. As x approaches positive infinity, f of x increases without bound. And in symbolic form, we write as x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, f of x approaches positive infinity. The behavior of the graph of a function as the input values get very small as x approaches negative infinity and get very large as x approaches positive infinity is referred to as the end behavior of the function. We can use words or symbols to describe the end behavior. Figure 4 shows the end behavior of power functions in the form f of x equals kx raised to the nth power, where n is a non-negative integer depending on the power and the constant. Identifying polynomial functions. An oil pipeline burst in the Gulf of Mexico, causing an oil slick in a roughly circular shape. The slick is currently 24 miles in radius, but that radius is increasing by 8 miles each week. We want to write a formula for the area covered by the oil slick by combining two functions. The radius r of the spill depends on the number of weeks, w, that have passed. This relationship is linear, so r of w equals 24 plus aw. We can combine this with the formula for the area A of circle, A of r equals pi r squared, and composing these functions gives a formula for the area in terms of weeks. This formula is an example of a polynomial function. A polynomial function consists of either 0 or the sum of a finite number of non-zero terms, each of which is a product of a number called the coefficient of the term and a variable raised to a non-negative integer power. Polynomial functions. Let n be a non-negative integer. A polynomial function is a function that can be written in the form f of x equals a sub n x to the nth power plus, and so on, plus a sub 2 x to the squared power plus a sub 1 x plus a sub 0. This is called the general form of a polynomial function. Each a sub I is a coefficient and can be any real number other than 0. Each expression, a sub I, x raised to the I power, is a term of a polynomial function. Identifying the degree and leading coefficient of a polynomial function. Because of the form of a polynomial function, we can see an infinite variety in the number of terms and the power of the variable. Although the order of the terms in the polynomial function is not important for performing operations, we typically arrange the terms in descending order of power or in general form. The degree of the polynomial is the highest power of the variable that occurs in the polynomial, and it is the power of the first variable if the function is in general form. The leading term is the term containing the highest power of the variable or the term with the highest degree. The leading coefficient is the coefficient of the leading term. Identifying in behavior of polynomial functions. Knowing the degree of a polynomial function is useful in helping us predict its end behavior. To determine its end behavior, look at the leading term of the polynomial function. Because the power of the leading term is the highest, that term will grow significantly faster than the other terms as x gets very large or very small, so its behavior will dominate the graph. For any polynomial, the end behavior of the polynomial will match the end behavior of the power function consisting of the leading term. Identifying local behavior of polynomial functions. In addition to the end behavior of polynomial functions, we are also interested in what happens in the middle of the function. In particular, we are interested in locations where graph behavior changes. A turning point is a point at which the function values change from increasing to decreasing or decreasing to increasing. We are also interested in the intercepts as well as functions, and the y-intercept is the point at which the graph intersects the vertical axis. The point corresponds to the coordinate pair in which the input value is 0. Because a polynomial is a function, only one output value corresponds to each input value, so there can only be one y-intercept, and the x-intercepts occur at the input values that correspond to an output value of 0. It is possible to have more than one x-intercept. Intercepts and turning points of polynomial functions. A turning point of a graph is a point at which the graph changes direction from increasing to decreasing or decreasing to increasing. The y-intercept is the point at which the function has an input value of 0. The x-intercepts are the points at which the output value is 0. Intercepts and turning points of polynomials. A polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. Access these online resources for additional instruction and practice with power and polynomial functions. openstackscollege.org.